Hi everyone, I'm Chen Feng. Today I will introduce the work for crowd counting, FPNCC, Visual Pyramid Network for crowd counting. This is a joint work with Dingkang Liang, Yongchao Xu, and Xiang Bai. We are from Huazhong University of Science and Technology. I will introduce the work based on this outline, background, related work, the method, results, and our future work. We will also show some demo for you. Crowd counting is a task aims to count the people in each video frame or static image. Most crowd counting work directly leverage the CNN model to regress a density map. This map is generated by the accumulation of Gaussian functions, and the pixel value represents the people number in each pixel. The whole map is obtained by the sum of the density map. Even though CNN model have achieved great progresses, there still exist many challenges, such as scale variations, density variations, and illuminance variations. As shown in the image, the scale can vary a lot. This is in the low altitude, and this is from the high altitude. As for density variations, this is very dense, while this is a little bit sparse, as well as the illuminance. The illuminance can be very dark, and it can also be very light. One of the directions that many people consider are the scale variations currently. Our previous work, L2SM, aimed to force the variant scales into the similar level, which therefore helps the regression model improve the density map quality. The following work, autoscale, extends it into the pedestrian localization. Different from previous work that can only get number of the people, the autoscale can further get precise location of each people. We adopt a simple and effective IPN-like model as our baseline, which is used in our VisDrone autoscale. The model is based on VGG16, and we discard the last two pooling layers to preserve the spatial information and add a dilated convolution to largen the receptive field further. Then the features from different scales are fused together. Here, we also use two different loss, MSE loss and SSIM loss. The MSE loss help us get the density information, and the SSIM loss helps us preserve the structural information. We combine them together and train it end-to-end. The follows are the other techniques we apply. For example, we use different density map kernel size for different altitude. The higher the altitude, the kernel size is smaller. It can be observed that the larger kernel size of density map usually generates a large Gaussian blob. This can represent the scale of the people. Hence, we find this quite important in drone things because the altitude usually varies a lot and decide the scale of the people. As for VSDrone datasets, there are many dark things which is quite challenged for current model. Therefore, we adopt the random illuminance data computation. The main method is to force the illuminance into a similar level. For example, we calculate the mean of all the RGB image, which can be referred as illuminance level. Then we force the high level illuminance into the middle level, and vice versa. Also, it can be seen in the image. The gamma equals to 1 is the middle level, and the gamma equals to 0.5 is dark level, and this is the light level. We can force the dark level into the middle level, and we can also force the light level into the mid level. We also use some scale data computation. For example, we random scaling the original image, as well as we regenerate the ground truth density map, which can reduce overlaps. And after reduced overlaps, we find the regression of the model can become better. This is also demonstrated into our previous work, L2SM. Also, we add some random noise to enhance the robustness of our model. Here are our results. We get the first place in this challenge. In our future work, we mainly focused on the crowd-localization instead of only the counting people. For example, we hope to get the local minimum of the people, which can represent the people localization. And in our recent work, we replaced original density map into the distance map. This distance map can represent the precise location, and we find it is quite suitable for localization task. We will also further explore it, and we also hope some people can give up some suggestions. Here is our demo. As shown in the demo, we show different things such as dark things, and such as here, the higher altitude things, the scale of the people are very small. And our model can capture the very small people, as well as here, the high altitude. Here is also the high altitude things. Here is the dark things. As shown in the demo, for our human, we can even hardly to capture the people, but as for our model, we can get it. Here is also dark things demo. Here is a very high altitude. Here is the low level. As well as low level. Okay, this all is our presentation. Thanks for your attention and listening.